So very good afternoon. So now our next speaker is Professor Shamar Kumar Dash. He is a very well-known scientist with a lot of accolades. So he has more than 200 research papers in leading journals, and he is the fellow of all the academies here in India. And he will be talking about supramolecular aspects of oxometalates in the light of crystallography. So you have been doing the classes on crystallography, you have seen the soft matter aspect of crystallography. Now you will see aspects of application in oxometalates in crystallography. So please join me in welcoming Professor Shamar Dash. Thank
you. Good afternoon, everybody, and thank you so much for inviting me and for giving me this opportunity to speak about this very important aspect. Before I start, I must tell you that although I wrote in the light of crystallography, I am not crystallographer by training. I do inorganic chemistry and mostly the polyoxometalate compounds. But with crystallography, we know what is there, what kind of supramolecular interactions are there, how it is helpful to understand the system. Once you know by crystallography what is the system we got, then we can explore a lot of interesting chemistry application in the inorganic chemistry or materials chemistry. So already you know that what title I mean. So because I tell about crystallography and oxometalate means I mean polyoxometalate. So let me begin with, because many of you know that inorganic chemistry textbook, so when we say one chapter is there, isopolyion, heteropolyion, they are nowadays people coined as polyoxometalate. Okay, so this is I'm talking about polyoxometalate. Many oxo, and because mostly they are anionic in nature, that's why metalate, like sulfate, carbonate, that's a metalate. Now, the best example I have given here, that is this polyoxometalate known as phosphomolybdate. Okay, long back it was synthesized. Okay, crystallographically was characterized also many years back by the scientist called Kegin, K-E-G-G-I-N, Kegin. So that's why his name is called Kegin anion. Okay, now you may wonder why people choose this one, because when you do the BSc practical, the phosphate test, phosphate test, what we do, if you want to know is a phosphate or not, we take some molybdenum source, ammonium molybdate, heptamolybdate, sodium molybdate. If phosphate is there, we acidify, you end up with very nice, canary yellow color, precipitate immediately. So why it is formed? Because this cluster is formed. This is the reaction, overall reaction to get this. If you use really ammonium heptamolybdate and sodium disodium hydrogen phosphate, we acidify. You not necessarily have to put nitric acid. You can put also mineral acid, hydrochloric acid. You end up with this compound, and this is the crystal structure. This is the polyhedral representation. I'm not going detail, but definitely there are 12 octahedral MO6 units are there, then 8 share and cornerstone, and overall you get -3 charge. If you take into consideration +6 here, phosphorus +3, then you get the overall this. Sorry, phosphorus +5, then you get this cluster. And ammonium salt you can isolate that. Why I am talking about? Because crystallography helps us to understand the structure, and then applications you can see that. Okay, so one thing you must know, polyoxometalate if you want to synthesize, or this is a heteropolyion. Well, you have other than this, only molybdenum, you have another element like phosphorus, sometimes silicon, sometimes boron, that is called heteropolyion. If it is not there, only molybdenum and oxygen, is called isopolyion. Okay, so I am dealing with here one heteropolyion. What is the basis of formation of this oxometalate? Basis is, when you, let's say start with even heptamolybdate in water, it comes in first molybdate form, tetrahedral molybdate with there are 4 oxygen involved. Then it will be, you acidify, the lone pair of oxygen takes proton, it will form. Then finally the coordination get expanded from tetrahedral to octahedral. Then there some condensation happens. So from OH, what will come out? MO form. This is the basic how this cluster form. Okay, even this same thing happened in zeolite function also. If you remember zeolite Y, aluminum silicate, same thing, AlO, Si, SiO, Si, AlO, Al. So same basic reaction happens and you get the product here. So one thing is here, there is a limitation here. Polyoxometalate, if you want to synthesize fine, you can get lot of application, you can get crystal structure. But remember, when you do chemistry in water, because they are formed in acidic medium, you cannot deal this complex in alkaline medium, because reaction will go other way, it will be hydrolyzed and compound decompose, isn't it? So because it is formed acidified medium, you can go up to pH 6, at the most 7, some compounds stable in the neutral pH also, but definitely you cannot handle them in the alkaline medium. It will be decomposition. Now I will give you some representative example. What are the polyoxometalates known? Many, plenty of. I have chosen very versatile one. One is called link. This is called MO6-419. I told you isopoly and heteropoly. It is isopoly. There is no other element like phosphorus here. It is not there. One is decaphenatate. Very versatile. Very well known. If you take decaphenatate sodium phenadate water and acidify, you get nice orange crystal within few hours. Decaphenatate. You have preyatungstate, again isopolyanion. You have kegin, just now I told you, phosphorus kegin is the cobalt centered kegin. Cobalt instead of phosphorus, cobalt centered, tetrahedral cobalt, and WPO40. I like to draw your attention about this compound much because I will tell you more story about this compound. Okay. And very interestingly, recently we saw this compound, if you can encapsulate in a confined space, it gets hydrolyzed to COW12O44. Remember, it is COW12O40, 3 minus. If it gets hydrolyzed, it will form COW12O44, 14 minus. Okay, that we recently saw by crystallography. And other than this range of clusters, you can get also very big cluster, medium size MO36 cluster. We have also very big cluster MO154, giant clusters, discovered in Posaki Muller's lab, where Somojiza, we all same lab. Okay, so we have some experience how to synthesize this big giant cluster also. So these are the representative example of polyoxometalate clusters. And I like to draw your attention about this compound particularly because this compound, we have done recent time lot of research, lot of interesting applications also. Now, what we do with this polyoxometalate compound? We do lot of water splitting, mainly electrocatalytic. Recently we started photocatalytic also, but today I will talk about mainly electrocatalytic water splitting. Okay, you know that in the electrochemical cell, the anode you get oxygen, in the cathode you get hydrogen, and you see the fundamental reaction of this half equation. They're not very easy. You need a very good catalyst to get it happen, and in nature it happens. Water splitting in the photosystem too. In the photosynthesis, one manganese oxocluster is there. Tetranuclear oxocluster. That is the catalyst to do that. So I'm talking about we need some catalyst to do that. Now, today I tell you mainly polyoxometalate centric some systems, mainly supramolecular chemistry. And supramolecular means if you want to know, you have to know what is structure actually by crystallography. So the compound I am showing you, mostly we characterize by single crystal crystallography. Mostly, some of them we could not. In that case, we have to take help of the PXRD matching and all these things. So I talk about complete encapsulation because you have a frame of material. You can completely encapsulate your active species, and you can do some interesting applications. You can attach a cluster surface some active species. Let's say I know one tensile metal aqua complex is very active. You cannot handle just like that because it will dimerize all this thing. But if you ordinate covalently attach to the cluster, it will be heterogeneous, insoluble, you can do catalysis. And also interestingly, an intercalation chemistry, intercalate between the MO3 layer, the graphite-like MO3 layer, you can intercalate some of the active species, you can see interesting chemistry. Again, intercalation we knew by crystallography. And of course, sometimes we also do just coulombic interaction, supramolecular interaction. They are not encapsulated, they are not intercalated, just they are side by side, but by hydrogen bonding interaction they are remaining and they give fantastic properties which otherwise not possible. So, today I talk one very interesting story about this polyoxometalate and this metal aqua complex. These together, the supramolecular interaction, how they make very interesting chemistry. Now, let me begin with one very interesting complete encapsulation host gas system. What I mean is that I told you some time back one cobalt Kagan, the cobalt center Kagan, this is the structure. In the center, cobalt tetrahedral W12O46 minus. This cluster is known long time back to those people. Okay. In fact, this Z-plate, what I am telling you, is also known. It is nothing unknown. It is originally one Chinese group synthesized, then it became popular. Omoyagi group, popularized, and they gave the name Z-plate. Okay. Now, what we found, when we take electrochemistry of this particular Kagan, known Kagan, it gives cobalt 2,3 couple. The blue. Cobalt 2 goes to cobalt 3. This fundamental chemistry, I must tell you, cobalt 2, we cannot make here cobalt 4. Not happened. We have checked by detailed electrochemistry, only give cobalt 3 to couple. Okay, very interesting. If you want to temper it, let's say very high, alkaline phase, you decompose. I already told you, any polyoxometalate alkaline phase decompose. If you want to very high potential, it can go to +4, but it will be decomposed. It will not remain Kagan structure. Kagan is very particular, tetrahedral, 4-oxo, then you get 12WO6 connected by H-sharing corner cell. So that if you want to temper it by doing forcefully, it will decompose. But it's very otherwise very stable structure. Because it's give 2-3 couple, we wanted to check when you put inside the confined space, what happens? These are main idea. Interesting thing is this cavity, this internal cavity diameter, it is 11.4 angstrom. And if you check from here to here, it is around 10.8 angstrom. That means size matches. Not that we first time we did. It was known by a British group that not this Kagan, silicon Kagan was put in this mode. Why we took? We took the cobalt is the redox factor. This is the idea. So we took that and we encapsulated. How do we encapsulate it? You cannot do just like that because there is no just window or pore it will go inside. Okay. Although size fits, but it cannot go inside. You have to do in situ. That means zinc and 2-imidazole ligand, if we just mix in the alcohol, this framework forms very easily. So what we did, we pre-synthesize, we first synthesize this compound, potassium salt, okay, water soluble. Then it is also soluble in the partly in alcohol, methanol. Then in situ synthesis we apply. In situ means we took zinc 2+, zinc salt, and we took that 2-imidazole ligand, and we kept this compound here. So when the MOP form, metal-organic framework form, some of them will be get encapsulated. Now let me tell you, we don't have the control of the encapsulation. Control means what? We cannot say that I want all cages should be filled. No. Whatever way we did, you always find that one compound, one cluster goes in 7 cages. So it is happened like that. The compound, this is a compound form. We have kept less amount, more amount, but if we put very less amount, we cannot get all filled. But generally, we get one cluster per 7 cages. That we characterize. We don't get single crystal for that. For this one, we got always microcrystalline compound, PXRD, all these things, and characteristic property of this. We prove that this compound got encapsulated one cluster per 7 cages. Okay. Now, let me tell you interesting things. As such, Kagan gives 2-3 couple. Okay? Cobalt 2-2-3. No oxygen evaluation. Once we put inside, the feature completely changed. You see, whenever you get the huge current surge, that is oxygen bubble come, and we can say the oxygen is formed. Not only that, this compound see continuous oxygen bubbling like 24 hours, all these things, and it works in a neutral pH. Now I told you the Kagan compound, polyoxometalates compound, they are generally decomposed. In alkaline medium, definitely it will decompose. Neutral medium it may decompose, but because we encapsulate it, nothing happens. 24 hours, you give oxygen. Again, you keep the same electrode use after 7 days. You can continue the same thing. Which is the heterogeneous system. What we do, we coat on the electrode. Let me tell you, heterogeneous how we do. The material water insoluble, we coat on the working electrode with some carbon material, and Nafion we use for binder, and it will be coated nicely, then it will not come out. Then we do the electrochemistry. And what we do, we find out 3 parameters: periodic efficiency, and turnover frequency, and overpotential. Overpotential should be very low, like within 300, 400 millimolar. This is a good catalyst. Periodic efficiency should be 90%. There is no other reaction going on. And of course we check the stability, how stable it is. So, very, very surprising thing, as such the compound giving 2-3 couple, 3 to cobalt 3 to couple, but this compound, when we put inside, suddenly what happens? It is giving oxygen bubble. Question come to us, because we are inorganic chemists. Then maybe something happened, the cluster got decomposed, but inside in the cavity, if it decomposes also, it will be evenly like that, because we characterize everything, we are getting electron spectrum, all these things. Then recent time what happens is, we found, it is this very recent time, when we published this paper, we wrote that only, that as if this, cobalt W12O40 inside the cake earlier. Recent time, we put this, same cluster, another mob. Okay, copper MOP 199. It is BTC, benzene triclosan, very, very well known MOP. So in this case, we got crystal structure, single crystal. We could, of course, very high symmetry in this thing, and then we found we could locate this, cluster inside. Earlier study we could not get single crystal, only PX study. Here we could locate, and there we found that it was tetrahedrally bound earlier, that cobalt 4, but here we found 8. Cobalt is connected to 8 oxygen, as if it is inside a cube. Then naturally, question comes, we also find like that. I mean, let's say these oxygens, tetrahedral oxygens are disordered over 2 positions. If one oxygen is half occupancy, G's over 2 position, it will look like it will be octahedral. Okay. But in this case, we checked 2-3 times again, we measured the crystal, we got full occupancy of each oxygen. We really actually happened that cube of 100. I mean, a cube, then cobalt is in the center. That means if chemistry has to happen, it will hydrolyze. Hydrolysis is what? Cobalt W4 46 minus water, and it will form cobalt W4O44, 14 minus and 8H plus. Okay. Then still we are not comfortable, because when I submit the paper, definitely somebody will ask question, we are dealing with disorder, all these things, who knows. Then recently we found 2-3 papers appeared, and they got same thing what we got. So that means earlier paper what we published, what we thought it is cobalt W12 O40, we strongly believe it was cobalt W12 O44, because now we check carefully Raman and all this study, the Raman spectrality difference between this and this. But the Raman spectrum we are getting now of the encapsulated one look like very much this, where I could not get crystal structure earlier on. So we believe that this is the compound form, and that give both couple cobalt 2 to 3, 3 to 4. Okay, now it makes sense why upon encapsulation it gives oxygen evaluation by electrochemistry, because we believe that the cobalt cluster hydrolyzed to this cluster, and now this gives 2 couple, cobalt 2,3 and cobalt 4,3 and cobalt 3,2. Now you may ask me, how do you know this compound will give these 2 couple? Because now it is published by others. we synthesize this compound and do the CV of that compound, and that gives exactly the, we got CV here, no, like that. That means definitely in our earlier paper, what we published before, although we thought it is nothing but that cobalt 2, that cluster, the cobalt 2 WnO14, it is not O, it is O14. Okay. So that gives the continuous oxygen. So that is very interesting encapsulation happened. And here is the very powerful tool crystallography. Unless we did not know this thing, we would not know the earlier case of this happened. Okay. So this way story begins, and you can see how encapsulation makes difference. A compound which is electrochemically inactive towards water oxidation, it gives water oxidation but by getting hydrolysis. And we found out all these parameters, turnover frequency, 10.8 mole of oxygen per second is not bad. Fatty resistance is very good, close to 100%. So it's a good catalyst and work in neutral pH. Now, because I am talking about polyoxometalate, you saw there that the central cobalt became active because it hydrolyzed and it gives 4, 3 and 3 carbon. Now I am telling about another interesting polyoxometalate. We could get single crystal. You see? Let me tell you what is this again, same again, SiW12O14, but you could take out one WO. Okay, then it will be SiWO39. So we take it out now to put the another metal, bismuth and water, these two water. So bismuth you can put if you can make it lacunary. What is lacunary again? If you take out one WO from SiW12O14, it will be SiW11O39, and that lacunary place you add on another metal, heteroatom bismuth, and you get this compound. Now we are lucky enough, we got the single crystal structure of this. Remember, now we are talking about bismuth in the periphery, not in the center. Center is actually silicon, but bismuth in the periphery. So by single crystal structure we found out, and this compound we wanted to do some chemistry. Why? Because although silicon again as such is not very active towards any water splitting or anything, because bismuth is there, bismuth 3 can go to bismuth 4, can go to bismuth 5, and you can get water oxidation. So that's why we started. But problem is, this compound highly water soluble, first of all, and again, this particular compound, when you put in water, neutral pH slowly decomposes. Because polyoxometalate already told you, alkaline pH decomposes immediately, instantaneously. Neutral pH also sometimes slowly goes. But this compound, this is a problem. This is what we thought. Earlier we thought you can encapsulate this compound in the same mop. So what we did, we take the same mop, Z paint, because these are size fit nicely. And why we did that? Because this bismuth, as inorganic chemists, we know bismuth 3 if you start, it can go up until bismuth 5 also by 2 electron oxidation, and that is very active towards water oxidation. It will oxidize water, come back to bismuth 3 and oxidate. So having that idea, we encapsulated there. Why encapsulate I told you? Because it is highly water soluble and decomposes with few minutes. So once you put inside the this same zip, it is very stable. It doesn't decompose. It is first of all heterogeneous now. It is not soluble because it is inside. If you remember earlier, I told you the cluster was 1 cluster per 7 kgs. Here it was 2 cluster per 7 kgs. Again, we have no control. Even if we put extra, it always takes in this particular case 2 cluster per 7 kgs. So we have kept one functionalized bismuth. Form polyoxometalate. How we functionalize with bismuth as well. Why we did that? Whole moiety is inactive, but bismuth is very active, and we can get water oxidation. Not only that, a miracle happens. The compound which is decomposed neutral pH slowly within 15 minutes or so, it is stable here forever. Forever means at least weeks and weeks and month and month. Nothing happens once you put inside. Then we wanted to check really electrochemistry, water oxidation. Now you see, very interesting thing happens. We can use in a very wide pH range from pH 4 to 7 to pH 13. pH 13, one polyoxometalate, you cannot imagine it will decompose. it will be happening, just come back of monomeric oxo and molecule of tungsten. But here you can do with 100 cycle pH 13, you can do the neutral pH 500 cycle, you can do even 1000 cycle in the pH 4. pH 4 makes sense. Polyoxometalates very stable. So he also get decomposed. After 100 cycles, slowly it hydrolyzed. Something happened because bismuth is here, no? Slowly attacked. But you can see in the same platform, in 100 cycle, you can do fantastic chemistry, water oxidation in the wide pH range. This is interesting material in the sense the polyoxometalate compound instantaneously decompose in alkaline pH. Here you can get stable catalysis for this 100 cycle. Now, so that was the approach. I am showing only very briefly few examples. There are many examples like that. Now, I'll show you the attachment, coordinate covalent attachment. Let's say you have a cluster, same Kagan cluster, and you have a aqua compound, let's say nickel, bipyridyl, and water. Water ligand is very important because water ligand, when there, then only when you oxidize, it will form hydroxo and double bond O to make active species. That's why water ligand is very important. So what we did last, many years since I joined University of Hyderabad, we are doing a lot of polyoxometalate clusters, crystallography, supramolecular chemistry. But we never checked water oxidation because we did not know that. So recently we were trying to check, and what we found that this compound you can make potassium salt, water soluble. You can get ready-made, nickel, bipyridyl 2 chloride salt, water soluble. To attach coordinate covalent bond as if the cluster acting as the ligand, isn't it? Oxygen lone pair coordinate to the by lone pair to the metal atom and make a very stable heterogeneous system, water insoluble. Now this compound, if you coat on the electrode surface, if we do water oxidation, let us see. Again, fundamental inorganic chemistry, nickel bipyridyl. I told you water ligand is very important. That will oxidize to water. Then Lewis acidity increase, so it will be one proton will come out. Then hydroxo, one more electron oxidize, nickel 4 will form. Again more Lewis acidity, and it will be one more proton come and we got nickel 4 oxo, and that will be very active towards oxidation. It will give continuous cyclic manner. It will give bubbling of oxygen, and again we got very interesting parameters like what we wanted to have. That radioactive efficiency close to 90%, very good turnover frequency, and decent, and I must say very good over potential, decent over potential. You can make it cycle. We also did the CP and cyclic stability to 1000 cycle. It almost same, little bit different because oxygen gas come out, some code may come out. That's a time little bit different. So you can do like that. Very interestingly, nickel compound give water oxidation. Now when we do copper. Similar bipyridyl copper, the same Kagan compound. We get, hydrogen evolution. Why? This is the beauty of metal ion, between the cobalt and copper. Copper case, definitely when we get water oxidation, metal has to go to hydrogen state, isn't it? Nickel goes to nickel 3, nickel 4, coming back to negative. Copper will get hydrogen evolution. We don't get oxygen. Gas comes when we put in the GC. We see hydrogen happening in the cathodic window. We believe that we should respect that soft and hard acid-base principle because copper is soft in nature and couple of micron ligand is there. So it will like to be reduced rather than be oxidized because soft nature. So cobalt 2 will go to cobalt 1 and cobalt 1 will be very good reducted. It will reduce proton and give the hydrogen. This is the idea. Now one may argue with me that maybe I am getting elemental cobalt, maybe compound get decomposed, the cobalt 2 becoming cobalt 0, and cobalt 0 is a good catalyst for hydrogen evolution, everybody knows that. But then we did a lot of control experiment. After electrolysis, we checked that material and we found no elemental copper. This cobalt always we find copper 2 only. So copper 1 form very unstable manner, very active, and immediately reduce the hydrogen to H plus 2 proton. That's why any resting time, you say if you do this, XPS, everything, you get copper 2. So similar system, when you put there is a coordinate covalent bond, you get continuous hydrogen evaluation, very stable catalyst, you can get that. So interesting intrinsic nature of the metal makes this difference. We did a lot of control experiment, of course, because you may say that if copper bipyridine aqua compound attaching the remaining same or not, but it may detach during the catalysis. So we did a lot of control experiment, and we proved that only during attachment time it is stable and give continuous hydrogen evolution. Otherwise, critical mixture doesn't give. What I mean by critical mixture? You may take copper acetate, you may take copper chloride and bipyridine, mix together in a grind together and do the catalysis. It will not give. So this is the story of the heterogeneous system by attachment, coordinate covalent bond attachment. Now again I have to thanks to crystallography, because by crystal structure we discovered something very interesting. What is that? This story of intercalation story MO03. Okay, let me tell you, because we do our MSc class practical, and there's one test called molybdenum. Sometimes we do test for tungsten. For molybdenum test, what we do, let's say sodium molybdenate you take in water, highly water soluble, drop wise you add hydrochloric acid, you get after some time some precipitation settled in the bottom. That is nothing but the molybdic acid, isn't it? This molybdic acid, very well known. If you heat it, you get MO03, molybdenum oxide. Molybdenum oxide, again alpha MO3, epsilon MO3, metaphase, and one hexagonal MO3, another state. But thermodynamic stable state is the alpha MO3. Okay. Alpha is a very versatile compound. If you write in a search engine like SciFinder, just MO3, I am not saying alpha, in a MO3, you get close to 50% hit. Where there is 50%, 50,000 papers published on MO3. Very, very versatile. That means MO3, people use a lot of sensing application, catalysis, all these things. So you also want to do something. Again, this particular story happened serendipitous. We got crystal structure, then we came to know the story. So what we let me tell you also in this context something called molybdenum bronze. Molybdenum bronze you get in a textbook level inorganic chemistry book. It was discovered in Germany more than 100 years ago, 1896. What is molybdenum bronze? This MO3, it is a water insoluble, neutral molecule, no? Molybdenum plus 6 oxygen state, and every oxygen 2 minus 2 minus 2 minus minus 6, so neutral molecule. The flame extended structure, graphite structure, neutral. If you put in water, you get suspension. That means every MO3 compound is water insoluble. Now, if you reduce the suspension with sodium borohydride or sodium diethionite, let's take the suspension and add sodium borohydride or sodium diethionite, reducing agent. Immediately you get some, very nice red-brown lustrous color. That means something happened. What happened? That it was neutral molecule, now it is reduced. Molecule 6 goes to molecule 5. So molecule 6 is D0 system, molecule 5 is D1 system, equal active system. So it is a mixed valent layer now. So that is minus charge now. To counterbalance the minus charge, negative charge, you need some cation. So sodium aqua compound get intercalated here. This is called molybdenum bronze. If you use potassium diethionite, you get potassium aqua compound. Lithium diethionite, you get lithium. So all are called molybdenum bronze. That means what is molybdenum bronze? Reduced MO3 intercalating alkali metal aqua compound called molybdenum bronze. Why bronze? They are shiny, lustrous, and they are electrically conductive. That's why it is molybdenum bronze. Although it was discovered in more than 100 years ago, 1896, alkali metal aqua compound is known, but one transition metal compound like copper or cobalt or nickel was not known. There we could contribute. We were lucky enough. Why it was not known, we did not know. We could get that again by single crystal crystallography. We just for MSc lab practical same thing we use. Sodium molybdenate HCl, we use acetic acid and we use nickel. Although I write like that, it is actually nickel chloride 6H2. Formula, if you write in the bottle C in any lab, in nickel chloride dot 6H2O. Actually, if you put in water, that form nickel hexaqua chloride. It's a covalent complex. So, just mix them together. Within 6 hours, you can get nice brown color crystals, and the crystal, we solved the structure, we found out that MO3 in between nickel aqua complex, and it is not molybdenum bronze, by the way, because they are not reduced. I didn't put any reducing agent. Because it is plus charge, something has to be there to counterbalance charge, so acetate get coordinate here. Okay. In the asymmetric unit, it is like that. The MO2O6, one acetate, and 0.5 times, half of the nickel aqua compound and half of the water. So, sorry, one water. That means to make our life easy to understand what we do, when we write the reaction, we make it double. Without MO4, O12, 2 acetate, now one nickel full compound, because this will make it double, so this is the compound. So we have single crystal structure, this is the compound, and to our surprise, all MO3 compounds water insoluble. This compound is water soluble. This is very surprising, but all MO3 compound water insoluble is soluble. What is the logical explanation? We believe, we don't know the answer because we didn't do any computation so far, that because some electrolyte is there, because nickel aqua compound and acetate kind of electrolyte, that may be make possible to solubilize the whole system. So it is a MO3 compound, not molybdenum bronze so far, intercalating nickel aqua compound, and it is water soluble. Not only that, if you dissolve the compound in water, pH becomes 3.8. Water pH 7, no? pH becomes 3.8. That means the compound is inorganic acid. Isn't it? Why it is happening? Definitely, when you dissolve, some proton comes out. If proton has to come out, what is the possible thing? Definitely some deprotonation of the water. When inorganic chemist, we did acid-base titration, and we found out that one of the water actually get deprotonated and it formed like that. So in the solution, the compound will get nickel, penta-aqua, 1 OH. Okay. So this compound formed, and that's why it is acidic in nature. Then we wanted to do electrochemistry, because we know that nickel aqua compound is electrically active. So this is the some structural parameters. It is a titanic system. This is the, I told you, the asymmetric unit is the dimeric unit, and this I make some structure to show you the fully hydrogen bonding. Please, I like to draw your attention on this hydrogen bonding structure. See, aqua compound and oxo of the cluster and water, highly hydrogen bonding. And that hydrogen bonding makes some difference that I am telling you the story. What is the story? I told you nickel aqua compound you can get easily from your bottle, from your lab, because it is nothing but the nickel chloride, NiCl2.6H2, this compound only. This compound, if you take CV, you get this feature, one red feature, and after some time you get deposition. It is water soluble. But if you do electrochemistry for several cycles, you get deposition on the electrode and this give water oxidation. After some time, oxidation stops because those particles get agglomerate, then no catalysis. But nickel chloride, if you oxidize in water, homogeneous solution, you get electrodeposition of nickel oxide. It is nothing but nickel oxide, this red feature. And it gives water oxidation. That means nickel goes to nickel 3 plus state, 4 state, then give water oxidation. Once it is there in the intercalated in the MO3, what compound you got, likely this is also water soluble. I told you pH goes down. That when we do CV, what we found? Completely miracle. This same person, same species giving water oxidation, here we get continuously hydrogen evaluation. Doesn't give anything on the right side, in the anodic side, it gives only hydrogen. We measure by GC mass, is hydrogen, pakka. Then why it is happening? Because here nickel 2 goes to nickel 3, 4. Why it is not going nickel 3, nickel 4, not water oxidation? Instead, we get hydrogen evaluation. That means, again, one has to do computation study, theory, we did not do that. By logic of inorganic chemistry, what we explained when the reviewer asked that due to strong hydrogen bonding, the electron density or electron around the nickel get reduced. The nickel amount of electricity drifted from metal side goes to by hydrogen bonding. So nickel center become like electron hungry, like to be prone to be reduced, isn't it? So that's why maybe that gives the, reduce easily nickel 2 to nickel 1 and gives the water reaction. Again question comes, so nickel 2 may goes to nickel 0 because we are getting hydrogen evaluation. We did control experiment, we did not get any, nickel 0. It is always nickel 2. So nickel 2 went to nickel 1 and nickel 1 reduced the proton to hydrogen. But let me tell you, it is not homogeneous. We started with homogeneous, but slowly some electrodeposition happens on the electrode. What is that compound? That compound we characterize now. So this is the compound originally in aqueous solution. Now this is the deposited compound we characterize, and this is the actually catalyst that gives the hydrogen evaluation. So what we believe that molybdenum C is equals to 5, but that remains same even after when you do the XPS. But nickel 2 goes to nickel 1 and nickel 1 reduce water. I come back to nickel 2 and make the cycle. So I'd like to draw your attention that this compound is the material what is deposited, and is also not anymore MO3, it is a MO3 but molybdenum bronze. It is now mixed valent, and the compound was, color was different, now became very shiny, lustrous color. So it is a molybdenum bronze but intercalating nickel aqua hydroxy compound. This is the compound we characterized by different studies. It took 6 months to characterize because we don't get single crystal structure of this compound, the deposited material. Then we did the, all sorts of, characterization, and we could do the, all parameters. Once we got nickel, what about cobalt? So cobalt also we did that. Same structure we got. We thought same thing happening, like, cobalt. In this case also pH comes down, that this is inorganic acid. But then the electrode deposited material, we get hydrogen evaluation, plenty continuous hydrogen, it is a better catalyst than earlier one. Then to find out why it is so good catalyst, when we found out the material, it is not anymore just mononuclear, cobalt compound. It is become to cobalt hydroxide. That means cobalt hydroxide and that to beta hydroxide integrated between the MO3, and that is the now catalyst for HER, hydrogen evaluation. Now you may ask me few things. We are doing electrocatalysis in the low pH, pH 3.84. I told inorganic acid, and that making cobalt hydroxide. Is not very surprising. To get cobalt hydroxide, you have to take cobalt salt and you have to make NaOH or KOH. Then you get cobalt hydroxide. And cobalt hydroxide 2 times, alpha and beta. Alpha is more expanded, beta is little compressed. The extended structure. In this case, we get beta. Makes sense because it is in the intercalated. You may ask me, maybe that if it is beta form, it will come out, physical mixture. The beta hydroxide and MO3 they are side by side. It is intercalated. We check by px because 2 angle will shift the lower side if it is intercalated. So that way, we prove even in the acidic medium, you can generate beta cobalt hydroxide intercalated. It is also molybdenum bronze now because some of the MO in the reduced state and is a very shiny color, lustrous. In the continuous, hydrogen evaluation, day and day, week and week, nothing happened. And once it deposited on the electrode. So this single crystal of the parent compound, like that, again it is tracking system like nickel 1, and in this case also the acidic unit I am showing here in the thermal plot, and this is the other integration compound. So I again tell you that very surprising that cobalt chloride, if you take from the bottle, it will give water oxidation OER, but in your case when it is in the layer, it becomes molybdenum bronze, it gives hydrogen HER. And these are the parameters. Okay, I almost reached my last part of my talk. So far, I told you about heterogeneous catalysis. Even the compound was soluble in earlier case, but it became deposited, it became heterogeneous finally. Now I am telling you very interesting supramolecular chemistry. Again, lot of help of single crystal exocrystallography and mixed valent cation also. This is not mixed valent, mixed cation. Cobalt gives 4+ charge and potassium gives 2 plus 6 and this 6 minus 7 because decaphenyl is the 6 minus charge. So this compound as such you can synthesize. In fact, you buy from already this is so stable. It is very very important compound because biologically active compound. Okay. What is this? The same thing I told you, cobalt hexagon COCl2 dot 6H2O. So these two compounds, as if I put in a crystal, no? So you may this compound, if you put in water, it gives homogeneous water oxidation. If it is really true and that too homogeneous, then why you have to make this? You take sodium bicarbonate, you take cobalt chloride and put in this proportion, you should get continuous oxygen. Doesn't come. This is the beauty of supramolecular chemistry. Why? When we solve the crystal structure, we found very very interesting hydrogen bonding network between this cobalt aqua and decaphenyl. Not only that, we took the mass spectrum of that. Okay? And same mass is getting maintained. What I mean is that whatever species we find, same mass we got. We believe that the compound there in the solid state, when we dissolve in the water, it is remaining the same hydrogen bonded structure. That is why a synergy gets established and this gives continuous water oxidation. So the synergy between cobalt and cluster by hydrogen bonding very important. What I mean? Again, let me tell you, maybe you missed it. I am telling this compound of single crystal structure. If you see the structure, you have cobalt aqua compound, which is right there. You have decaphenyl cluster. That means if you mix them, they should give water oxidation, but they don't give. Only the compound we got single crystal, that we dissolve, that give water oxidation. That means the crystal structure is maintained in the solution and that gives the water oxidation. So these are the crystal parameters. I just took it from there. And then we did a lot of study, Raman and crystallography, PX30, telling that everything fine. Only thing we proved that whatever solid state is there, in solution remaining same hydrogen bonded structure, we check by mass spectroscopy. Then we did the electrocatalysis. I will not go through all these details because that's like what you take out, but I forgot to take out. We wanted to tell you a synergy between cobalt and decaphenyl established, and that synergy gives this job. Now question is that why synergy happened, how it happened. They like to tell you. Okay. So a compound, because in this case, sorry, I'll take just almost done. Let me go back to here. Because this system, when I explain anyway, is to confuse that I'm telling you again and again that this compound doesn't give water reduction, this compound doesn't give water reduction. In fact, we already know this compound, if you take this, it gives water oxidation. I told you already for some time, the cobalt oxide form. This can give, in principle, can give water, hydrogen. Because vanadium 5 goes to vanadium 1 and give hydrogen. We check, doesn't give. The whole this compound gives. But is again, there is no coordinate covalent bond, no covalent bond, only hydrogen bond. Okay? The hydrogen bond. Hydrogen bonding I am showing here. Now, a system, if you want to give hydrogen evaluation, something has to be reduced, either cobalt, 2 has to go to cobalt 1 or cobalt 0, whatever it is, or decaphenyl has to be reduced, vanadium 6 to 5, then they can reduce the proton to hydrogen. As such, they are not giving, separate they are not giving. Even physical mixture was not giving. If we physical mixture not giving. So what we did, we wanted to know what is the active site. Then we took the help of, in another, I tell you that one trademark that any homogeneous electrocatalysis, you have to check that make sure there is no deposition happening. I told you many times, if you start with homogeneous, then after some time it gets deposited, and then finally that is the catalyst. Homogeneous electrocatalysis means You have to do after 100 cycle, 500 cycle. Again, you check the surface by microscopy. It will be same. There is no deposition. So that we also did to prove it is homogeneous. Electrochemical. Homogeneous is very rarely happen in soil. The maximum case it gets deposition. Then I went to my colleague who does computation to know that actually what is the active site, cobalt or vanadium. Vanadium 5 can go vanadium 4, cobalt 2. So we requested to do some calculation. Calculation shows very interesting. I am not I don't do computation. Qualitatively I understood from my collaborator. My colleague student actually did that. My colleague student did that. So this is the homo-lumo gap of the cluster. Okay. Now cobalt 2 will have two spin states. Cobalt, alpha state, beta state. Beta state gap is smaller than the alpha state. And if you see that now our compound, the compound we got single crystal. For alpha state, this is the gap, and for beta state, beta spin, this is that means beta spin is the better, synergy established when you get this. They talk each other because vanadium cluster and cobalt system talk each other. A synergy established, then only it happens. Now, how it happens, I like to tell you. Electrochemistry, machine will give some electron. The electron will be taken by what? Cluster will be taken first, or cobalt will be taken first. That you want to know. Now, we see that LUMO is delocalized here, and SOMO is single occupied. So we found that in the case of cluster, the LUMO is electronicity occupied line with the vanadium cluster. That means when machine give electron, the vanadium will first reduce. And we believe that electron goes to cobalt. Cobalt 2 becomes cobalt 1, and then cobalt 1 reduce the water to hydrogen. This is from the theory. So that means synergy definitely established, because as such I told you, as such compound doesn't give water reduction, as such cobalt doesn't give water reduction, even physical mixture doesn't give. That means physical mixture doesn't establish synergy, because hydrogen bonding establishes the synergy, and finally we can get hydrogen. So electron come from cluster from machine to cluster to cobalt to water. This way get continuous hydrogen. So this is the thing I want to tell you, that polyoxometalates, oxometalates, you can understand first of all. If you are lucky, you get single crystal, you know what is the system. You know the system, you apply your mind and do interesting chemistry. So we found that is a cobalt 2, it can go to cobalt 3, but many times interesting happen. When intercalated cobalt aqua compound as such give water oxidation, if you are intercalated, it is not giving you hydrogen. That means how powerful is supramolecular chemistry, hydrogen bonding interaction. That MO3, electron drifting happen from the metal side, become electron hungry. That's why like to reduce, giving hydrogen. As such, cobalt chloride giving oxygen. So a lot of things can be understood if you have lucky that you get single crystal structure. You understand first from the structure, and you can do the chemistry. Thank you so much for your attention. Please.
So now we would like to move on to our question answering session. So, yeah.
Hello. Very nice talk, sir. I have few questions and few query you can say. For your HER and OER part, actually I have seen that you have mentioned the value of overpotential is around, it's really high. For OER it's around, I think, for MOF 199 it's around 790 millivolt, and for cobalt cases HER it was around 365. So it's quite high. So how we can control this kind of
case, I
potentials?
can tell you the MOF. I did not show you some result. The MOF conventional then neutral demo. We got it in the first paper, no, 700 something. Neutral demo. We believe the same thing. You go ask also, but they only answer, because the MOF is neutral type of framework. if you can manage to put inside some conductive electro carrier, you can improve. One paper we published in inorganic chemistry after some time, after that paper, we put one KG as electron carrier inside. So that 700 something went down to 465. So because of the nuclear nature of the mock, high, what would you say? We could not improve unless you put some inside electron. That can be done. So it is what we understood. If you can manage to put some conductive material inside, you can improve the water resistance. And in the case of intercalation, we always good. We get always within 300 millivolt water resistance because that always there in the conductive nature. It is not that like a neutral thermometer. No? And in fact, that molybdenum now reduced. So molybdenum bronze happening. No, so that helped to make the water resistance less.
Yes, sir. And one question more actually. In one of your slides, I have seen that you are using cobalt chloride and like things. And in an intermediate, beta cobalt hydroxide is forming. So how you confirm that in the reaction media?
Yes. You also thought it's a beta mononuclear cobalt compound like nickel.
Yes.
Nickel case is a mononuclear, 5 water coordinate and 1 hydroxy. So when we got the deposition, this is the lustrous compound, fine, very shiny material. When we took, now we always make more compound on them. We take and we send for XPS, we send for all sorts of kind. For TEM, from fringe gap we could it is definitely not mononuclear found out. Mononuclear is a characteristic electron spectrum also. Then we found out it is a cobalt hydroxide. We also didn't believe first because being in the low pH, pH 3.84. But then, if you think the basic inorganic chemistry, in that cathodic potential, when it's going, that condensation happens, and that's why it is forming. And then we found out it is cobalt, from the TM study, it is cobalt hydroxide, but then alpha or beta. Then what is beta from the exact, that gap. Interesting thing is, it also makes sense why it is beta because first we thought it is a physical mixture, that maybe beta cobalt hydroxide form, cobalt hydroxide and MO3 side by side. But then it was intercalated because PXRT that we identified 002 peak, that is shifting left side. Okay, so and beta is the compressed one and alpha is the elongated one. And because it is the intercalated nature, that's why maybe it is beta form actually. So TM study help and other two study help from actually Raman leakage different from the alpha and beta. So that we take out from there and we did rigorous study. Actually it took a lot of time to characterize this compound. And it is now mixed valent compound also. It is a molybdenum reduced. But that doesn't matter. That doesn't give hydrogen. Only that cobalt. And another interesting thing is cobalt beta hydroxide also known from if you put cobalt chloride and then add on the sodium hydroxide, you get beta. Two ways you can put. Zeolite Y supported cobalt hydroxide we make alpha. That gives water, oxidation. Beta also gives water oxidation photohydrology. For P.K. Datta shown from, Ohio State University. But this same beta cobalt hydroxide giving hydrogen innovation. So it's very, confused. Then we realize because the compressed nature and electrons, again electron drifting from the metal side, instead of oxidation, it got reduced. So definitely cobalt 2 goes to cobalt 1 and that done. But they never goes to cobalt 0 by then. That is, people may think not cobalt 0 easily give hydrogen, but then we never saw. We did a quantum experiment, we sent sample for X-rays, we never got cobalt 0. Either cobalt 2 and cobalt 3 in the case of zones.
Yes, sir. Thank you so much, sir.
Have you got any more questions? Sir?
Good evening, sir. So my question is that in one of the slides you showed that the window aperture of the host structure, that is ZIF8, it was written that the window aperture is smaller than the gating structure. So is that the window aperture, it represents the whole cavity hole of the zip 8 structure? That is the host.
Now telling you, zip 8 internal cavity diameter is 11.2 to 3 angstrom. Okay, and whatever compound we use from one end to another 10.8 angstrom. It is not easy to encapsulate inside unless you do in situ, because zip is formed by organic ligand and zinc chloride. So that you put, and your your POM you already keep, or the POM cluster, polyoxometalates cluster already synthesized, keep in the in situ. So when MOP is forming, is taking inside the cavity. Once it inside that, it cannot come out because no aperture, no windows. But only problem is you don't understand the loading level. Some case you get 1 cluster per 7 kg, some case you get 2 clusters per 7 kg. The loading level, so far we didn't understand. Even if you put more also, but one way is good. Full loading level is not good because electron transport will not be facile. So anywhere you have to get the full, electron transport facile, then only you can get all this, reaction. So the low loading level is good, what we got. But why it is happening just like that without our control, that we don't understand.
And so one more question, sir. If the point was written that window aperture of zip 8 is smaller than the Kagan, smaller than the Kagan structure. That means Kagan structure is bigger in size than the zip 8.
That's what I'm telling you. That's why once you form in situ inside, it cannot come out. It's entered like seed in a bottle. In situ means what? Tell me. I am putting zinc 2 and organic ligand, 2-metazole ligand. These two form the MOP will form with big cavity. Forget about small aperture, window. Now, our compounds already there. We already put the compound in the medium. So what is forming the MOP is picking from the solution and putting inside. So aperture may be small, no problem. It's small good for us, it will not come out.
Okay.
Here, one more paper I did not tell you. Let's say cobalt aqua compound, you can do with zeolite. Zeolite, why you know that? 13 angstrom super cage and going to 7 angstrom. Okay, cobalt aqua compound, 1 into 1 and 4.5 angstrom. There, if you put inside, it comes out. Because window is 7 angstrom. Even inside 13 angstrom cage, cobalt mononuclear compound inside, you put that KOH or NaOH, cobalt aqua compound come out and hydroxide a layer form on film form on the surface. That's why the aperture is very important. In that case, aperture small, window small, so it cannot come. So you have to put in situ, then only get inside there.
Okay, thank you, sir.
Any more?
Any more questions? If not, then we will have a small announcement. So please proceed.
Please join me in welcoming Professor Karidasanan to the stage to present the token of appreciation on behalf of Gyan Course and ISET Kolkata to Professor Samar Kumar Das. And Professor Roy, you can also.
Oh, that is there. I'll help you. You like that? Thank you. We have followed together. We have. Thank you so much.